Yeah.
The quarry yesterday, and our dogs our youngest are about the same age. Well, she only has one.
Yeah.
Clipper, as they're playing, like doing the zoomies.
Yeah.
Well, that happened.
And she is broken ankle, broken knee.
Oh my God! Oh no! Did she fall? Or?
So she,
Oh, no.
we were walking.
Yeah.
Am I on mic?
Nope.
Okay.
You good?
Oh, okay.
Yeah.
We were walking, and they tend to just like barrel.
Of course, yeah.
Whatever. They're just a force. They're
Yeah,
coming
of course.
Anyway, so we were walking, and we always, when they come, just get in a sports stance.
Yeah.
Because we're gonna likely get clipped. I took a step to my right, and she went to follow me right, and was in sports stance. She followed me right like this, but they clipped her here, so she went like, so it like spun her, but this foot was planted. So it was just like us. And so I was on her right. I saw it all happen.
Oh.
And I was like, okay, can I say swear?
You're muted.
She
You're good.
fucked up her knee.
Oh.
But like, there's no way I thought there was breaking. There was no popping. There was no
Yeah. Oh.
crunching. It was just like, but I saw it, Joe.
Oh.
And I'm like, in my head, I'm like, she fucked up.
That
So
sucks.
she fell to the ground. I'm like, Kenny, what do you need me to do? She's like, call an ambulance. I broke my leg. In my head, I'm like, I don't think she broke her leg.
And she broke her leg.
She did, like, not just.
How long did it take the ambulance to get there?
So they were quite quick, even
Yeah.
though she wasn't a priority call.
Yeah.
But the problem was you have to get through a gate that's locked
Yeah.
to get in there. So the issue was getting the gate open. But at least they got there and got me to get her some blankets and a survival blanket and stuff, because she was lying on like the rock hard cold path. Like, it's not a cement path, even that would be cold, but it was like dirty, just lying on the ground. And she's like, I'm so cold. And of course her body was in shock.
Yeah. Oh my God, that is
Oh my God,
awful.
so this poor girl.
So I didn't break your foot, but she broke her
No,
leg.
I know,
Oh
and,
my
and in
God.
my head I was just complaining about how much my foot was bugging me. And here's the other thing, I have only told a few people this.
Yeah.
We're walking, and her boys went to go skating on the ice. So there's a little group of high school boys ahead of us, because they walked.
I wish I knew it was so funny.
And the dogs were zoom, zoom, and I'm like, isn't it funny that the dogs don't have the common sense not to go into that group of boys?
Yeah.
Like they bang into us. And Kim's like, yeah, or they probably know, like, oh, it's way more fun to bang the old biddies because it'll break a hip. So she just said that, like 20 minutes earlier, and then they bonked
And then
her.
she broke her leg.
In 2 places.
That's crazy.
No, 3. The ankle, the tibia, and a little bit of her knee bone. Anyway.
Yeah, I got her on this. That's crazy. Wow. Well, thank you for sharing.
Well, I'm
That's
sorry
nuts.
to share that, but I was like,
Ugh.
it's just the craziest thing.
What are the odds? Yeah, that's wild.
Bye, my friend.
Bye. Guys, sorry about that. I was just, Ms. Bainbridge just came in to tell me the craziest story. I'm not dying, no, I promise. Anyway, she and a friend went for a walk yesterday, and it ended with like ambulances and broken legs and all kind of craziness. So anyway, sorry about that. Am I back on? Can everyone hear me now? No, you can't hear me?
Yes.
Okay, good.
We can hear you, we're just not talking.
Ryan, did you just say that was a good start again? Oh, I'm so ashamed. Okay, well today, in our good start to the day, we're going to do a lab. And obviously, you aren't here, so I'm going to have to do it, and you're just going to have to collect the data. But we're going to try to learn something about the relationship between pressure and some other things. So we know that eventually we're going to start building this relationship into chemistry. And at its most basic, we know that if you pump more gas in, you're going to get more pressure, right? So more gas equals more pressure. But gases behave strangely. So if you remember yesterday, we looked at temperature, or temperature. We looked at pressure and the units it's measured in, and then we also looked at temperature and the units it is measured in. So I want to take a quick look at that, and we can kind of take up our little tiny bit of, I hesitate to even call it homework, because it was really just something to look at. But so here's what we talked about yesterday, and we said that once we know how many moles of gas we have, we'll be able to figure that out on the basis of volume and pressure, and we eventually discovered temperature, that these are the related things, that temperature, pressure, and volume all relate to one another, as well as how much gas you have. But we said that, first of all, pressure has a bunch of different units we measure it in. We can measure it in PSI, which is what you will see if you're a mechanic or a structural engineer or a carpenter, PSI. We can measure it in millimeters of mercury, which is what a barometer will tell you. So if you're a weather person, if you're running a weather station where they use a barometer, that's the unit we're going to see. And then in SI, if you're a physics guy, if you're an engineer doing theoretical engineering or things like that, or a chemist, we measure it in kilopascals. That's the unit we use. And then, for convenience sake, and it is very convenient, we say, well, since 101.3 kilopascals or 14.7 psi or 760 millimeters of mercury is the pressure in like a normal room, just hanging out, then they define that as 1 atmosphere. So there's a crazy number of units we can use for this. It sucks, it's annoying, but having this table at the ready is going to be helpful because you definitely are going to have to do some unit conversions with pressure. It's going to come up. But we said it kind of gets worse because temperature has a units problem too. What is the problem with both Celsius and Fahrenheit as units of temperature?
Not accurate.
Yeah, and not accurate in a very specific way, which, yeah, Preston, very good. Specifically, the problem with them is that they have this false zero. They have a 0 degrees, which really just means, hey, it's cold, right? Like 0 Celsius and 0 Fahrenheit, those are cold days. They both relate to freezing of water, which is a thing we deal with. But 0 should mean none. It should mean 0. And something that is 0 Celsius doesn't have 0 heat. Something that is 0 Fahrenheit doesn't have 0 heat. That's right. Terusha says 0 doesn't actually mean 0 because the particles is still moving, and that's what heat and temperature is. So we use a unit called Kelvin, which is the same as Celsius. It uses Celsius as its base. The only difference is they shift the 0 down so that 0 really does mean 0. 0 Kelvin would actually mean no temperature at all, no heat, no movement of particles, a state we call absolute 0. And what is that adjustment factor? What do you have to move Celsius by so that 0 really means 0? Anybody? Yeah, 273.15. And you said 272 or so. That's pretty close. But yeah, 273.15 is the number. So, if we want to adjust from Celsius to Kelvin or from Kelvin to Celsius, it just requires an adjustment of 273.15. So really quickly, what would 22.5 Celsius be? Very good. Very good, Tashante. And how do we get that? Well, to go from Celsius to Kelvin, we have to add 273.15. And if we add 22.5 to that, we get 295.65. And the only quibble I would have is, if we're thinking sig figs, when we add, what do we do with sig figs? When we add, what do we do with sig figs? Well, since I don't have all day, when we add, we look at decimal place. Ah, very good, the lowest number of decimal places. And since this only has one decimal place, our answer can only have one decimal place. And we would say then 295.6 Kelvin. And just remember that's not sig figs. We don't count sig figs when we're adding and subtracting. We look at decimal place. All right, 376 Kelvin. What would that be in degrees Celsius?
What Preston said.
Well, yeah, what Preston said, but again, when we're adding and subtracting, we're going to subtract 273.15. Well, if we look at decimal places, do I even need to look at that 0.15?
Oh, so 103.
Yeah, very good. There's no point including the 0.15 because that's more precise than the number I'm starting with. So just match the precision. And so we'd say, yeah, 103. 103 degrees Celsius is 376 Kelvin. What does water boil at? By the way, water boils at 100.00000 degrees Celsius because that is like the definition of 100 Celsius.
373.15.
Yeah, so we can
Kelvin.
keep as many decimals on that as we want. And just remember again, I think you said it right, so I'm not criticizing, but we don't say degrees Kelvin, we just say Kelvin. Very good. Did anyone look up what the hottest day ever recorded in Medicine Hat, Alberta was?
Medicine Hat, Alberta. Wait, my mic is on.
Yeah, it's a place. It's a place. I didn't make it. Tashante gives me an answer, 315.35 Kelvin. So let's work back. What was the hottest day ever in Medicine Hat? What would we do to work back to Celsius? We'd do 315.35 minus 273.15. And 5 minus 5 is 0. 3 minus 1 is 2. 31 is going to give us 30. 15. 15 minus 3 is... Oh, I didn't need to do that. I had a bigger number up top. 5 minus 3 is 2. 11 minus 7 is 4. So 42.2 degrees Celsius. Whoa. That's a hot day. That was a warm day. Don't like days like that. Do you bet you didn't know that was a place? Yeah. Isn't it? And I think it's a really good name for a place. Come on.
Medicine Hat, best name.
Yeah, it's good. It's a good name. And I'm not saying you should name your firstborn child that, Elizabeth, but Medicine Hat Brady doesn't sound bad now, does it? So there you go. The surface of our sun is 5,000... Yeah, Monopoly Canadian edition. By the way, Tashante, did you by chance get the date on that? Ooh, Nathan got a 143.9. Depending on sources you look at, they measure things, depending on where they've measured them. I wonder if it was recently. Because for most places, the hottest days on record occur in the last few years for obvious reasons of climate change. Anyway, the surface of our sun is 5,800 Kelvin. What is the surface temperature of our sun in degrees Celsius? And again, to me, if we're 5,800, and by the way, if you looked up a more accurate temperature for the sun, you'll get a different answer from this. But just because there are more accurate answers, I shouldn't say more accurate, more precise. But going off this, we would subtract 273. But really, would we subtract 273? Because again, we would just say that there's no point being more accurate in our conversion than we were in our original. So really, this is just going to be 5,500. And again, if you had a more accurate, a more precise starting temperature, you could go to a more precise answer. But 5,500 Kelvin would be the correct answer from this, because we're working to the nearest 100 on the basis of this temperature. Questions about any of those? And again, I'm seeing Preston's number. And again, you obviously started with a different number, right? Because 5563 plus 273 won't give you 5,800. Right? Like if we did 5,800 minus 273, we would get 5 minus 2 is 3, 9, 10, 7. We'd get 53. Oh, I screwed something up though. What am I doing? That, why would I turn that to a 5? We'd get 5527. So 5,500. And yeah, Tushante went all the way to 2 decimal places, gave us 5226.65. That's great too, but again, just make sure you round so that you're only as accurate as your starting number. And again, if you started with a more accurate, or a more precise, I should say, starting number, then great. You'll just have a more precise final answer than we do, which there's nothing wrong with that. Okay, questions about that before we move on? Okay, today we're going to look at the relationship between temperature and pressure. And we're going to do that in a highly scientific manner. I'm going to do this in the best way I can, which is I have set up here I have set up here a little lab apparatus. Don't be too alarmed by the hands or anything like that. This is basically a beaker, a flask inside of a beaker with water, and then the flask has 2 sensors hooked up to it. It has a thermometer, and it has a pressure sensor. So it has to stay sealed, and that will likely be where this all falls apart for us, because if anything isn't perfectly sealed, then we will lose pressure, and in losing pressure, we will get inaccurate data. But what we're going to do is we're going to measure the temperature and the pressure of this as we go over time as we crank the temperature up. And while we do that, we'll also take a note and talk about it. So I'm going to share my screen again, and I will show you the software that we're using to do this. It's not especially sophisticated, but that's okay. So we're using a piece of software called Lite. And Logger is a nice little piece of software that will track the information coming out of these probes. So can everyone see my screen right now?
Maybe.
That's not...
Yes, I can see.
Okay, and I've tried to make the lines a little bigger. So right now it's telling us that the temperature inside my sealed flask is about 23.5, and that the pressure inside that flask is about 99.7, give or take, 8 kilopascals. Okay. What I'm going to do is I'm going to start collecting data, and I don't need to take 2 samples every second. I think probably taking a sample every 2 seconds would be more than sufficient. And we'll take it for 1,200 seconds. What's that? 120 would be 2 minutes. So this is upwards of 20 minutes, which is good. Okay, so now we're going to do that. Now, we probably won't get perfect data here. Why have I put it in water like this rather than just put the hot pad right, or the hot plate right on the beaker, or the flask rather? Why would I heat water, put this in the water, and then I had to put like a bunch of screws and stuff so it wouldn't just float on top of the water? Why do all that? Anybody? Because normally when I do this lab, I put a bunch of equipment on the bench and I say, figure it out, guys. I want this relationship. And so now today I had to figure it out. So this is my kind of half-baked little method. I just want to make sure, by the way, everyone can hear me, yes?
Yes.
Okay, good. Because I moved stuff around, so I wasn't 100% sure. So why do we put it in the water? What's the purpose of that? Why do we put it in the water? Well, I'll tell you why. I put it in the water because I'm worried that if I just put it right on the hot plate, the bottom would get hot and the air down there would heat up and you'd get the pressure rising, but the temperature up here wouldn't have risen as much yet, and we'd get data that didn't quite match. So my thinking is that if we put it in the water, that will even out the heat. If anyone's ever baked like a cheesecake and they use a bain-marie, a water bath in the oven, it's the same basic principle. Now, again, our data may still suck, but here's what I'm going to do. I'm going to press collect, and then I'm just going to dime the temperature on this. And this is probably not going to be like super exciting data. Let's be clear about that. But I will set this to auto scale as we go, and to auto scale as we go. And I'll set this to auto scale and to auto scale as we go. And so we'll keep checking back in on this. My assumption is that we won't see much of anything for a little bit because it's going to take some time for that water to heat up. All right, so we will periodically check back in with our lab data as we go. Does that make sense? There we go. So you can actually see what.
Come on, let's get to 100 kilopascals.
Sorry?
Come on, let's get to 100 kilopascals.
Yeah, it will. And like I said, this data isn't going to mean much of anything to begin with. It actually shows our temperature going down right now, which probably has, I mean, these are fairly accurate stuff, so there probably is something to that. And it could be as easy as the air in there that is hot is rising and the cool air is sinking as we're getting a differential in there. I don't know, but I wouldn't track the data to mean much of anything until we've got, you know, a temperature that's moved up to 30, 35, 40 degrees. So for now, we're just going to kind of leave it be. But we can see the temperature is starting to go up now. And I can tell you that the plate is getting warm. So that's good. So we'll let that do its thing. And while it's doing its thing, we'll take a look here. Okay.
100, yes.
Okay, so I'm going to slide that over so you can't see it for now. I'm going to point my camera back at me, and then we'll check in on this as we go and see if we can get the type of data we'd like. I will note that it will be a real coup d'etat for high school science if we get nice looking data for this, because this is not actually easy stuff to get nice looking data for. All right, back to me. Okay, so while that's happening, let's talk. So can everyone see the note in front of me now?
Yep.
Great. Okay. So with the note in front of me, let's talk.
I'm putting
about
50
this.
E-Sail bucks on pressure winning.
On pressure winning? Is it a race?
It's some sort of competition.
Well, here's a question. Do you think there would ever be a time where the temperature number would be a higher number than the pressure number? Anyway.
Depends on what units you're using.
Yeah, good answer. Okay, so let's take a look at this. So today, we are eventually going to do chemistry using gases. We know that more gas, more moles that is, will affect the volume, right? Because in a balloon, if you pump more gas in, what happens to the balloon?
The balloon gets bigger.
Good, the volume gets bigger. So we know that more gas will affect the volume of a gas. More moles, we increase moles, we'll increase volume. But we also know, what if we're not using a balloon, but we're using a tank, a steel tank that is not going to get any bigger? As we pump more gas into that, more moles isn't going to mean more volume because that tank container is really rigid. In that case, what's going to change?
Pressure?
Yeah, will affect the volume and the pressure of a gas. And then we also know that the temperature of a gas changes its volume and pressure. So what we need to do is we need to work out the relationships of these things. We need to work out the mathematical relationship between volume and pressure and temperature and all of these other things. By the way, just to check in, They are rising together nicely. So that's encouraging. We'll get some kind of data out of this. I'm curious to see, we'll end up with quite a bit of data. We've already collected 215 samples. Yeah, I'll be curious to see what kind of data we end up with. We'll find out. So, over the next couple days, we will explore the relationships between volume, pressure, temperature, and the number of moles. Okay, I'll give you a minute to write that. Does anyone have any questions so far about kind of where we're headed with this? Okay, the first relationship we're going to look at is the relationship between temperature and pressure. And just at a cursory glance, looking really, really, really simply, let's take a look at the data we've collected so far. Whoa. Okay, just at a glance, who could describe in really broad terms the nature of this relationship for me?
When one goes up, the other goes up. I forget the word to describe that.
Sure, that's okay. So as one goes up, let's call one of them temperature. As temperature goes up, the pressure does what? Also goes up. We call this a positive relationship. Now, that means that there is some level of math that can be done with these numbers. So let's take the numbers we have so far. And I'm gonna do my best to get them here. I'm gonna open Excel. I'm gonna open a new book in Excel. Oh, interesting. Sorry, I'm gonna do a little bit of copying and pasting. And let me start by saying that that is annoying that it won't let me copy that. Let's try 1 second. I'm going to stop collecting for a second, and hopefully I can continue collecting in the same data table, but if not, I will have copied and pasted it, so give me a second. Experiment. Data collection. Continuous. Okay, well, I've got append to latest. There we go. Okay. Sorry about that. I have cracked the code. Okay, so I've got here, so far, the data we're looking at thus far. So I've got, in this column, what do you think the 23.489 is? What are we measuring there?
Temperature.
Very good. And what would that be measured in?
Degrees
Celsius.
Celsius.
Great. And the pressure in?
KPI. Not K.
Yeah, very good.
AP.
Yep, that's good. Kilopascals. Now, what temperature should we want to work with? Do we typically like Celsius as chemists? What's the problem with Celsius?
0.
Yeah. So I want the temperature in Kelvin.
Kelvin.
Very good. What am I
Like
going to do
two
here? I'm
people
going to
have
say
said.
take the Celsius temperature, and what do I have to do to make it Kelvin?
At 273.15. Oh, we almost got to 404 data points.
Orlando, I think you might be muted, I guess. Your mic's not, you can't hear anything.
Great way to continue the third part of the day. Now I can hear you.
Yeah, we can hear you just fine now.
Yes. $92%. Pressure. Oh, temperature.
It's temperature.
I love how there's so many circles that it covers up the temperature. $22.115. There would be no pressure. Zero. You need that to make this one look like garbage? I'm joking. No, that's exactly how I am.
Orlando, you're just that scary.
He's tough, it's the first thing you notice about him. Unless he's just talking to a piece of... He's just talking on a... Okay, that's actually a pretty cool fun fact, though. And the glass completely changes shape. It's just like vaguely familiar. I was gonna say letters, but that works too. What do you mean might have? What a good name for a law, though. What a good name. Nice, his name is Joe. No. Unless you're Caleb, then yes.
I was about to say it depends on who you're asking.
That's off. That's perfect. T2 equals 60 degrees Celsius.
Orlando, are you over your time? Because I just got a call. Okay, I just got a call from my next class saying.
Nice roast.